How about now? Yes. Good morning. Hello, hello. Choo, choo, choo. Parametric cam, computational design, tutorials, live stream. Choo, choo, choo. As you can see, I may have overdone my coffee intake this morning, so just bear with me, because it might be a bumpy ride today. Dr. Manuel, I'm not sure if I've seen you before here. Very welcome to the channel. Michael Wickerson, so good to see you. How are you doing? And Nylan, welcome to you as well. Very happy to be amongst peers and friends and beautiful people who love computation, who love design, and who love being creative using technology, which is absolutely my jam. Totally my jam. So let me set up a couple things here and there. I need to open a couple. What do I need to do? I need to find this. I need to open this. I also need to get myself my cheat sheet here on the side. Oh, what? Today's exercise is going to be so cool. Like, so cool. Michael, how are you doing? You're also doing tutorials on YouTube, correct? Like, how is that going for you? Ah, it's intense, huh? I've seen some of yours. They're pretty cool. Good job. Where was I? Where was I? Yes, I'm looking for tutorials. No, what am I looking for? I'm looking for... What am I looking for, actually? Oh, I see. I see. All right. So just give me a couple of minutes. I'm kind of planning what we're about to do today. So, which is going to be, we're going to do, I think this morning we're going to do two extremely cool exercises. It's going to be taking a facade, triangulating the facade, and then laying those triangles flat on the ground or on the floor or the XY plane for, I don't know, for sending them where? For sending them for fabrication or for drafting or whatever that is. And I think we're also going to try to do the same thing, but with a surface. We're going to try to do the same thing with a three-dimensional surface. We're going to try to triangulate that surface and then lay the panels flat for fabrication, for drafting, or whatever. Elangoban, good morning. I'm not sure if I've seen you before on the chat, but very happy to have you here. Parastorm, good morning. Thank you for being here. How's everything doing? Michael, did you just use the P word in this channel? I don't know how I feel about this. And we don't use the P language here. I am absolutely joking, okay? Absolutely joking. Python is a very legit programming language. It's very useful. It's great. For some reason, the joke that I think I might be guilty for that. I think I'm kind of perpetuating that joke of Jose Luis doesn't like Python, so blah, 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 blah. But it's absolutely, I do Python myself sometimes. I get grumpy and mean, but I do it, and it's great. And definitely for machine learning, it's the real deal. But anyway, let's not get into that. Why are we getting into that? Why are we talking about Python so much? Good morning, Smith. I'm also not sure I've seen you before here, but welcome. Thanks for joining today. What are we doing? I think we're going to be doing that. What I don't know is what are we doing this afternoon? I'm out of, if we finish those 2 exercises in the morning, I'm kind of done with my cheat sheet. So I will need to sit down and plan what are we doing for the afternoon, which could be what? We're almost done. We're almost done with the playlist. Do you realize that? That would be great. I still want to do a little bit of work on intersections. I want to do a little bit of work on Boolean logic. I want to do a little bit of work on randomness. I want to talk about randomness and do a few exercises. I think it's important. We tend to use it a lot without in an uncontrolled way. But but I need to sit down and think what that could look like. Yeah, I don't know. I don't know how we're going to do that because I don't have time to do that before this afternoon. Well, let's just do these exercises here. Okay. Let's just do these exercises here. And once we do those exercises, then we're going to do those exercises, and then after that, we'll figure out what we do in the afternoon. Period. Raik, good to see you. How are you doing, sir? Hanye, welcome back. So let me do formal introduction. So hold on. 3, 2, 1. Hello, welcome. This is Jose Luis, and this is Parametric Camp. It's a side project of me that actually started with COVID. It's one of those good side things that have happened through this pandemic, because I woke up one day and I've been meaning to do these live streams, online YouTube thing for a long time, and we're all locked down. I have nothing to do, so why don't I just buy a green screen and then just do it, And then I will start doing this was very inspired by Daniel Shipman and the Coding Train, who I actually believe is live streaming right now. So if you folks who are now here would shift to the Coding Train and watch that live stream, I would not be offended because I really like Daniel and his work. But anyway, so this is Parametric Camp, and we do live streams where we discuss computational design and we record tutorials live. So what you're going to see today is me recording back and forth and blah blah blah, and then we take the live stream, we cut it, we edit it, and we publish it as more polished videos. We are currently in the midst of wrapping up a full new series called Introduction to Parametric Modeling. In that series, I'm basically explaining what is behind what's called algorithmic modeling, or in other words, creating three-dimensional form using rules as opposed to using static modeling. And we typically only stream on Fridays, but because I really wanted to get this series out of the door, we are we've been intensely streaming all last week and also this week. Now, if you like this channel, maybe you want to consider subscribing, hitting the like button on this video, turning on notifications to know when we go live. Otherwise, if you want to know when we go live, I typically post on social media. We have social media right there that you can follow us. I'm more of an Instagram person these days for some reason. You can also subscribe to our Google Calendar that I'm posting on the chat if you want to know when we go live. And we also have a Discord server that we use to have offline conversations when we are not streaming. And I'm actually very happy that I know many of the people who are on the chat right now from that community. So if you're interested in having offline conversations, feel free to join the server. There is a channel called Introductions where you can use a template to talk a little bit about yourself, who you are, why you're here, why you're interested in these things. And we also have a few other channels where people just post technical questions or they just engage in conversation. We have a bonfire because that's what you do when you go camping. You sit on the bonfire and you chat about stuff, So that's great. And what are we doing today? We are continuing with the Introduction to Parametric Modeling playlist. And we've been doing in the previous videos, we've been doing a lot of data manipulation, data tree manipulation, and seeing how we could generate geometry that involves matching different objects. So collections of points, collections of lines, etc. in a way that requires data manipulation. What we're going to do today in this live stream right now is we're going to do two exercises where we're going to apply these techniques. We're going to design a freeform facade, and because freeform is not typically fabricatable, we're going to discretize that facade in planar elements, so in triangles, and then we're going to do a simple reorientation operation to put all those triangles that are in 3D space and put them and lay them flat on the XY plane so that they can be drawn at the real scale, or they can be fabricated by a machine, whatever. Okay. And then I think we're going to do the same thing for in 3D. So shall we get started? Let's get started. So less talking and more coding, right? What is this? The Journal of Digital Landscape Architecture? Practical in digital landscape architecture will be presented these days at the DLA virtual conference. Oh, I had not seen this conference. Digital Landscape Conference. That's kind of cool. Huh. All right, this could be very useful for some of my students, actually. Okay. Can I subscribe to that? Do they have a newsletter or something? I don't know if they have a newsletter. Some of my students would really. I have a lot of Stephen Irvin. Oh, isn't he a GSD? Yes, I know Stephen. Ah, yeah, he is a. He works with us here at the GSD. Okay. Yeah, they don't have a subscription. DLA conference. Well, maybe they have a newsletter here or something that I can follow. Contact, Facebook, LinkedIn. Wait, it was in Boston last time? Are you kidding me? And this is Stephen. That's unfortunate. Virtual conference organized in Boston, I guess. No, well, the digital landscape. I kind of. Facebook? Who uses Facebook anymore? Ugh. And what about LinkedIn? Groups? Okay, maybe I'm just going to join this group. And ooh, I have 31 requests that I haven't fulfilled. Okay, sorry. I don't really use LinkedIn much anymore. Not at all, actually. Wonderful. Okay, sorry, I got distracted, but I typically, many of my students do, I have a lot of landscape students in my Introduction to Computational Design course at Harvard, and they typically do projects that inquire on some aspects of landscape, which is kind of nice. I wonder, is there any project from last year? So I don't know if you know, but all the projects of my students' projects are on this website, GSD 3363338. I wonder if any of them could be a good fit for publication there. This could be one. Interesting. This could be one too. This was also a super cool project actually. Anyway, sorry, I'm getting sidetracked here. Okay, so my drawing. Where is my drawing board? Okay, so I need to set up my drawing board. Raik, what is very nice, the landscape conference or my students' work? And then I'm going to, I hope I don't break anything. Fold this in here. And I'm going to do a wireless. How's student work site? I know, it is very nice. Thank you. I appreciate. I love my students' work a lot as well. They did really good this year, especially under the conditions, the remote conditions. Okay. And sketchbook. There you go. All right. And we are live. And I see people are posting questions already on the C# Grasshopper channel on Discord. So if anyone is able to help, that would be great. Okay, so what are we doing today? So I think what we're going to do is we are going to do this exercise where we're going to start okay, so we're going to do, what are we going to do? We are going to first design some kind of facade that is going to start off some kind of free-form surface. Like this, for example. Like this, and then what we're going to do is we're going to subdivide this. Now, what we want to achieve is something like the following. What we want to achieve is something like the following, where we're going to subdivide this, like this, like this, like this, and like this, and like this, and like this, like this, and like this, like this, and like this, and like this. That's going to be 1, 1, 1, 1, here, 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 here. But with the difference being that in this case, we would like this to be somehow solid, so it's not going to be just lines, right? So that's one thing. So we would like this to be surfaces. So you can see that the exercise is already going to be very similar in spirit, and then we will have to divide this, of course, into a bunch of points, okay? And then we have to divide this into a bunch of points, and then we would have to do a little bit of, you know, a little bit of data matching here. Now, how is that going to work? Well, we will see that during the exercise, but first we're going to do this part, blah, blah, blah. So that's what I'm thinking, what I'm going to say. So let's start the video. And then what I would like to do, yeah, I forgot to say, I would like to have the panels at some point. I would like to have them laid out like this. Something like this. And then okay. Choo-hoo! Okay, let's start. So let's get started. So what is it that we're going to do in this exercise? Well, the idea is that imagine we are designing some kind of free-form facade, and we're going to be using, for example, two curves to define that free-form facade. If we were to join those two curves with a loft, for example, we would get a NURBS curve, which has, as we know, like a really fluid geometry, curvature, etc., etc. But it turns out that if we were to make this in the real world, making a facade that follows the exact shape of a NURBS surface is actually very difficult in material terms, in the real physical world. So very often what we do is we follow processes of triangulation. And this is important because triangles, one of the characteristics that they have is that no matter how they are oriented in three-dimensional space, they are guaranteed to always be planar. And planar is very good in the physical world when we make physical things, because making planar things is actually really easy in the physical world, manufacturing planar stuff. Manufacturing curved stuff is very, very difficult and very costly. So very typically, even if we have a very fluid undulated facade, in the real world, what we do is we triangulate that facade into triangular panels, and then these are the panels that we use to cut them from glass or from wood or whatever, and to put them up in the physical world to approximate that that smooth surface, that smooth curvature. Now, and another process that is very common as well is that when you're modeling this in 3D, you always want to end up having a process where you take all these triangles that are in three-dimensional space, and that might be great, for example, for visualization, for rendering, for whatever. But if you want to actually make a model of that, or you want to send the drawings of those triangles to whoever is going to make them, to fabricate them, then having them perfectly orthogonal so that you can draft them in the real dimension, or you can cut them with a machine, is a very, very useful thing to do. So taking the triangles from three-dimensional space and flattening them into a planar XY plane for drawing or for fabrication is a very, very common operation, which is what we're going to be doing here in this exercise as well. So before we start with the whole ordeal of like the triangulation and whatever, the first thing that I would like to do is I would like to start and set myself up in Grasshopper. I'm going to create two curves, I'm going to subdivide them, and then we're going to start taking a look at how to join them with these triangles. So let's go to Grasshopper and let's get this set up, and then we can go back and discuss triangulation. All right, so let's do that. So I'm going to draw a curve here. I'm going to draw a curve here. Oh, that was a very not nice curve. Wait, what about this one? Ooh. Okay. And then I'm going to move this in Y. And then I'm just going to bring in the curve here. Set one curve, another curve. And then I'm going to loft them. Well, that I can do while I'm doing the exercise. Okay. That I can do while I'm doing the exercise. I'm going to put here some bifocals. For those of you who are still not using icons, seriously. And this is going to be the number of spans. Okay. And I'm going to let me empty this. All right. And this is going to be where am I going to put this? I'm going to put this in the desktop. So E18. Triangular facade, and this is going to be also E18. All right. I have gone ahead and created myself some stuff to start with. So I was in Rhino and I created these two curves that have that live in 3D space and that are a little bit far from each other, a little bit far from each other. And then I'm going to bring them into Grasshopper by using empty curve parameter components and then loading them with this information. And then I also created myself a slider with an integer to define how many spans are we going to be subdividing this facade into. The first thing that I'm going to do is I'm going to actually create the facade but just for visual flavor, because we actually don't really need this. So I just want to create the surface for kind of, again, visual flavor, but I don't actually need this at all, technically speaking. And then what I would like to do is I would like to subdivide each one of those curves into a series of spans. So that's going to be one subdivision, that's going to be the other subdivision, and the amount of spans is going to be equal to that parameter that I just specified. Okay, so having this, I think we are now ready to start taking a look at what can we do. And I'm actually going to hide the surface because really, we don't really need it. So let's take a look at what are we going to do for triangulation. Okay, so what are we going to do? So Parastorm, can you not see me? The live is turned off. What is happening? Can you not see me? I thought we were live. Are we live? Can everyone confirm that we're live? Can you hear me? Live, live. Can you hear me? Are we live? Works fine for me. Yes. All right. All right, cool. Thank you. Thank you. All right. So what are we going to do? How are we going to explain this? We are going to explain this. Hey, Hex. Hey, how you doing, sir? Barbara, welcome. Good to see you. And all right. So how are we going to do this? How are we going to explain this? So the first thing I want to explain is that in this case, we're not going to do individual bars because we're not going to do individual bars because we need triangles because we need the flat area. So the process is going to be very similar to what we've done in the previous exercises, but instead of bars, so line to line, we're going to do surfaces, which are going to be defined by 3 points. And therefore, what we need to do is we need to do a little bit of manipulation and group. Yes, so we're here. So because we need to create triangles like this. And then triangles like this. The first thing that we're going to do is that we will need to isolate. All the starting vertices, so those are going to be all of this. The starting vertices. Then we also need to then isolate the second vertices. Those are going to be this. All right, so those are going to be these ones here. Oh no, sorry. These are going to be these ones here. And then we will need to isolate, so that's going to be second point, and then the third one is going to be the ones that are here. This collection of points. And once we do that, we will be able to feed that to the we will be able to fill that to the surface, to the surface component. And the surface component is going to okay. Now, when it comes to triangulation, the techniques that we're going to be using are going to be essentially the same ones that we have used in the previous videos, where we did the trusses and we do like subgrouping of points and lists, etc. It's going to be very similar. The only difference is that in this exercise, because we want the triangulated elements, in this case, we're not going to be doing matching with lines between two lists of points. What we're going to be doing is we're going to be doing matching with triangular surfaces between 3 groups of points, so that we get this surface entity. And then the idea is that we're also going to be following very similar procedures as we did before. So for example, you can see that the way I have triangulated this surface, there are kind of 2 groups of triangles. Ones are the ones that start with the bottom left points, if you will, then they go to the right, and then they fit into the diagonal. That is like half of the triangles, and then the other half would use a different connection, a different matching logic. So the idea is that I'm going to do this in 2 steps. I'm going to do one family of triangles first, and then I'm going to do the other one. And the way I'm going to do that is by using this surface free form, and I'm going to be using this component that is called 4-point surface. I don't have 4 points because it's triangles, but this component actually works as well if I just feed it 3 points. So it creates a surface out of those 3 points. So now the problem that I need to resolve is, how do I select the 3 lists of points that I need to feed into that component? And that solution is going to be using the same techniques that we have seen before. So as you can see, for example, in my code, you can see that the starting points for each triangle are going to be this one, this one, this one, this one, and this one. Those are like the main vertices. So if we take it, those points are actually all the points that we have on the bottom, except for the last one. So if I find a way of taking the whole list of points and removing the last one, that collection will be the collection of points that are the starting vertex of all my points, of all my triangles. Now for the second points, you can see that the triangles always use this point here as the second point if we are going anti-clockwise, counterclockwise. So if I find a way of selecting all the points on the bottom, except for the first one, except for this one, that will be the second list of points that I need for my triangulation. And then you can see that it only follows that the third collection of points is going to be all the points on the top, except for the very last one. So what am I going to do? Very similar to what I did in the previous exercises. I'm going to take the points at the top and the points on the bottom. I'm going to do a little bit of list shifting or sublisting to remove the first and the last element, and then I'm going to use that to triangulate the surface. Let's take a look at how to do that. Remember that I like to be super OCD about about naming things, because when I do data, this is a very personal me, when I do data manipulation, I lose track of things very easily. So I'm going to put a box here that is going to contain points. Remember, this box doesn't really do anything, but just pass them through, if you will. And I'm going to right click and I'm going to type here bottom nodes, and I'm going to hit the paint bucket so that the name shows up on the component. And I'm going to copy and paste this, and I'm going to plug the other ones. And now I'm going to call this top nodes. Okay. All right. And now that I have them here very clearly in a group, now what I can do is I can now start working with the bottom ones, and then I can create a sublist that is going to contain all the points except for the last one. As usual, I'm going to drop here a point list so that I can see the numbers of the indices, and I have a clearer visual output of which points are contained in this particular list. So if you remember from my previous videos, I'm going to use the shifting technique to take all the points on this list, all right, and shift them by -1 unit, which will result in a list that contains the same points except for the last one. And what I'm going to do is I'm going to right click here, or I'm going to just create a panel where I'm going to type false to deactivate wrapping, so that by offsetting all the points 1 unit, I actually lose the last point because it's not wrapping the points anymore. I explained this in previous videos, so make sure to check that if you haven't so far. So these are all the points. So, and I'm going to write here very programmatically, bottom nodes minus minus last, for example. And then I'm going to copy and paste here, and I'm going to shift now 1 positive unit. And you're going to see that if I plug this in here, what I get is the same collection of points except for the first one. So this is going to be minus first. Correct. And then what I'm going to do now is I'm going to copy and paste the whole thing, and I'm going to feed this here, the top nodes. And then I'm going to visualize the top nodes here. So all of this I'm going to be the top nodes minus the last one, and these are going to be the top nodes minus the first. Is that correct? Yes, these are the top nodes minus the first one. Wonderful. So this has been a way of manipulating the data lists so that I now have data lists. I have collections of points where I'm missing either the first one or the last one. And it's going to be very useful for data matching. So before, what we did for data matching was we had the line component that takes two inputs and creates a line between, for example, the bottom minus the last and the top minus the last. Oops, and the top minus the last. And you can see that I get all these lines here. This component, the 4-point surface, is going to work very similar. I'm going to take, as per my diagram, I'm going to take the collection of all points minus the last, all points minus the first, and then at the top, all points minus the last. And I'm going to create a triangle using these three collections of points. So now I have bottom nodes minus the last one, bottom nodes minus the first one, and then top nodes minus the last one. And you can see, ta-da! I should do like Daniel Schiffman and have like some sound like, ta-da! Like magic. Magic just happened. So I have now this triangulation, the first family of triangulated vert panels in three-dimensional space. And now, obviously, I'm going to also use a 4-point surface to create the other triangulation, which is going to be what? It's going to be all these points here. So the triangulation is going to be, let me draw this here. Triangulation is going to be like this. I'm going to start here. This is not looking good. I'm going to start here. I'm going to join this one, and then back. So that's going to be this collection of points, the bottom minus the first, then this collection here, the top minus the first, and then this collection here, the top minus the last. This is very difficult to say actually, but it's easier to just see here that if I want to take all of this, so that's going to be bottom minus first, then all of this here, so top minus the last, so minus the first. So I want to take all these ones here. So that's going to be the second point. And the third point is going to be all the top nodes minus the last one. So that's going to be this one here. And now you can see that I have the two families of triangles. One is going to be the ones in the bottom, and the other ones are going to be the one that has a base in the top. And let's parameterize this. Now we have more spans, less spans, and technically, if we just crank this up a lot, then we will very much approximate the actual NURBS curvature of the surface. But obviously, the more we define, the more difficult it would be to make in the real world. But also, the lower definition we have, you can see that it's kind of not, it doesn't look great. So for the real world, we will need to find some kind of middle ground it's easy to make, but still kind of satisfies the original curvature. Whatever. Okay. Wonderful. So now we have the two families of triangulated points or triangulated facade elements. Now what we need to do is we need to take them from 3D space and we need to lay them down flat on the XY plane. How are we going to do that? That's actually going to be a piece of cake. Let's take a look at that. Hi, Saeed. Welcome. how are we going to do this? How am I going to explain this? What I want to explain is that I want to take this, oopsies. I want to take this and move it here, this and move it here, this here, here and here, and then I will want to do the same thing, a second operation like that. So in order to do that, we know the reorientation operation, but the orientation operation requires a source plane and a target plane. So the target plane is just very easy. We can just generate here like a grid of 2D planes. Okay, I can explain that, I think, pretty easily. So how are we going to do this? Well, what we want to do conceptually is we have all our triangles in 3D space with whichever orientation they have in three-dimensional space. We don't really know that yet. And what I want to do is each one of them, I want to lay it flat in XYZ, in XY. And we already discussed this is really good for drafting, for drawing, for measuring, and for machines that make these things physical, that they fabricate these things. So we will probably have to do 2 operations where we take the bottom triangles and we lay them flat, and the top ones and we lay them flat. But how can we lay them flat? What kind of operation is that actually? Well, taking something that has a particular orientation in 3-dimensional space and ends up with another orientation in 3-dimensional space, whether be it flat or not, it doesn't really matter. We have already seen that one operation that was really useful for that, and you heard me talk about how I think it's the MVP of transformation, is the orientation, the reorientation, or the change of basis, which is an operation that takes an object and takes a reference plane and a target plane, and then moves the object from that reference plane into the target plane. So what that means is that in order to do this, we will need to somehow figure out for each particular triangle, we will need to figure out which reference plane we use for the source, the orientation, and which target plane are we going to be moving it to. For the target, I would say it's going to be pretty easy, because what we can do is we can just generate here at the corners, we can generate a set of planes on XY, and we already know how to create, for example, 1-dimensional arrays or 2-dimensional arrays of elements. So we can just do this numerically. But so for the target ones, but for the source ones, it's going to be slightly more complicated because we don't really know where these elements are in 3D space. So we're going to have to come up with some way of figuring out where those planes that I have drawn flat would be in 3-dimensional space, so that they contain those triangles in a planar way. And actually, due to how we have worked so far, it's going to be super easy, because what I can do is I can try to generate, for each triangle, I can try to generate a plane that is based on this corner of the triangle, that is oriented towards the first point of the triangle, and then whose secondary axis also is oriented towards this other plane, to this other point. We have seen before how we can create planes out of 3 points, and therefore the result of that operation is going to give me some kind of plane that is oriented towards this first point, and where the second axis, the green one, is going to be oriented in a way that contains this point, and therefore, since the 3 points are going to be contained in that plane, the triangle is going to be contained in a planar way inside of that plane. And therefore, when we match this target, this plane as the source, to this plane as the target, this triangle is going to end up laying flat on the XY plane. All right? So, and then we will do a very similar operation, but for the triangles on top. So for the triangles on top, we will be able to create just like, I don't know, like this planes here based on the tip of the triangle, and we can also do those as an array. And then here we would use this point at the center of the plane. We will use this plane as this point as the main axis, and this other point we will use it as the secondary axis. For example, that can be a way to go. So shall we give this a try? Let's give it a try. Okay. All right. So we're going to go here. Mm-hmm. Okay. The first thing that I'm going to do is I'm going to actually create the source planes, the ones that are in 3D. This is actually going to be the easier part, surprisingly, because it's just going to be as easy as going to planes and then creating a plane from 3 points. So that plane from 3 points for these surfaces is going to basically follow the exact same matching pattern that we use for the surface. So for example, it's going to take the bottom nodes minus the last one as the origin. So that's going to be the origin of the planes. Then the first point for the orientation of the x-axis is going to be this collection of points here. So I'm going to feed that in there. And then the third point is going to be the one that we had on the top. So that's going to be this one here. And you can see, if you look closely, you can see that these planes are actually oriented in 3D space. Can you see how the plane very nicely fits this triangle here? And can you see how this other plane is very nicely fitting that triangle here? And so on and so on. So we have here now the origin planes that we're going to use for the transformation. Now the only thing that we need to do now is we need to create a one-dimensional array of planes, these ones here, that we're going to lay flat and that are going to be the target for reorienting the triangles into the ground, into the floor, or whatever, however you want to call that. How can I use that? How can I do that? It's actually going to be super easy. Let me create here somewhere, for example, here. Let me create a simple XY plane. So one plane that is just flat XY, and it's here. And now what I would like to do is I would like to copy this plane multiple times in the X direction at a control distance between them. How many times? As many times as triangles I have. How much distance? Whatever, a control distance. So then I'm going to do that. I'm going to do a parameter for that. So I'm going to type here, for example, spans, panel. I'm going to do panel separation, for example. And that's going to be part of my inputs now. And what I'm going to do now is that I'm going to copy this plane several times in the X direction. So what I'm going to do is I'm going to move this plane, because remember, moving in Grasshopper world actually means copying because it's implicit. I'm going to move that in the X direction, but each one of these X vectors needs to be multiplied by a series of numbers that go from 0 to however many elements we have at control intervals. We've seen in previous examples how we can generate a numerical series. For example, we can generate a numerical series that starts at 0, that has the step size is going to be how the distance between those panels. So that's going to be this distance. And the amount of values in the series is going to be the amount of spans. So that's going to be the amount of spans. You can see how, if I now take a look at this, you can see that I have 10 numbers going from 0 to 90 if I plug those into the x vector, I get 10 vectors from 0 to 90 in the x direction. And then if I use those to move the plane, I have generated a collection of 10 planes that are spaced apart 10 units. So what can I do now? Well, it's going to be just as easy as reorienting, going here, going to Euclidean, going to orient, and then I would like to orient these triangles, the triangles that I have in three-dimensional space. I'm going to like to orient these triangles. Then the source planes are going to be the ones that I just generated here. So those are going to be the initial planes, and the ones that I created here in the bottom are going to be the target planes. And you can see how, nada, we have laid all the triangles flat in the XY plane. Nice! That is very cool. And let me just move this a little bit out of the way here, and let me play a little bit with this panel separations kind of situation so that I can like squeeze them a little bit, which I kind of like. All right. Wonderful. So we have that. Now we need to do the same operation for the other ones. Now, what we could do is I could just create another plane here and do the exact same operation and have them laid out here as well. But since we kind of see that there's a certain order to how these panels are arranged, I may just want to increase this spacing and then add the panels here in between so that we have the bottom one and the top one, the bottom one and the top one, the bottom one and the top one, etc., etc. That could be an interesting thing to do. So the way to do that is actually going to be super easy. The only thing that we need to do is we need to find the planes here in 3D space, but we also need to create a series of planes here that are in the middle. So that's just going to be as easy as starting from a plane that is already halfway through here and then replicating that plane as many times as we have so far. So how can I do that? I'm going to take the original plane and I'm going to move it here one time, half the distance between the spans. So I'm going to move this plane in the x direction an amount equal to half the span. So I'm going to take the panel separation and I'm going to create an expression, of course, that is going to be x divided by 2. And then I'm going to plug that in here, and then I'm going to use that to fit the x component. All right, so now I have the plane here in the middle, and then I can also just copy that plane. I can take that one single plane and copy it in the x direction multiple times. How many times? The same amount of times that we did for the other planes, because the gap and the spacing and the amount of planes is the exact same one. So now I have the planes for my bottom panels and the target planes for my top panels. All right, so the only thing that I need now are going to be the planes here in the origin to use for the projection or the reorientation operation. So that's going to be very easy as well. I'm just going to create a plane with 3 points, and I'm going to follow the same logic that I followed for the surface. So I'm going to do bottom nodes first, then I'm going to go for top nodes minus the first one, and then top nodes for the last one. And I'm going to turn these planes off. And then you can see that the planes are in 3D space, and it is true that they are containing those panels. The only thing, and then if I use those panels, I use those planes to reorient the panels, I'm going to get this result. I'm going to orient the panels with this being the source and the new planes here being the target. And the result that I'm going to get is going to be something like this, which is a little strange. So let's take a look at what's going on. So for some reason, this triangle is not kind of oriented like this, but it has the tip here, and this is the long edge, and this is the diagonal edge, and it's kind of rotating 90 degrees, kind of. Why is that happening? Well, if you think about the way we join the points, or we fed the points to generate the plane, we use this as the first point, then we use this as the second one, and therefore the main orientation, the x orientation of the plane, is pointing this way. And then the third point is here for the secondary direction. So basically the planes are oriented in a way that the sharp tip of the panel is at the origin, and then the long vertical edge is in the main direction. And that is why here you can see that this triangle has the plane on the sharp tip, and then the vertical edge is in the main direction. So whether if we like that or not, it's up to us to decide, but perhaps something to make it more clear or more homogeneous with the orientation that we chose before, maybe for these panels, for these ones here, for these planes, we could choose a different way of orienting the planes. So to match how the previous ones were set, maybe what we can do is for the vertical panels, what we can do is we can set the plane on this corner. We can set this as the main orientation, and then the sharp tip can be the third point that just sets the secondary direction. The only thing that we're going to need is to just rewire how these planes are generated so that the origin point is this one, the main axis point is this one, and the third one is the other one. So I'm just going to disconnect everything, and I'm going to say the origin, so the input for A, is going to be all the points on the top minus the first. So that's going to be this one. The B, the orientation of the main axis, is going to be all the points on the top minus the last one. So that's going to be this one here. And then the sharp tip is going to be this one here. You can see that my planes are now oriented in 3D space with the origin here, the main direction this way, and then the sharp tip on the other end. And as I do that, you can see that now, all the panels have actually kind of rotated 180 degrees in space, and they all have the sharp tip, if you will, pointing upwards. So this would be the planes on the bottom, and all the ones here would be the planes on the top. Obviously, this is not guaranteeing in any way that there are no overlaps. So for example, if I actually choose to do, for example, less spans, you can see how they start overlapping. But if I should choose to do more spans, you choose how they overlap less, but there's more space in between them. So there are ways of making this process a little smarter, but we're not going to get into that in this exercise. All right? But this was, as you can see, we have basically taken all this geometry and we have laid it flat, and these panels are ready to just go into drafting or go into production, fabrication, or whatever you want to make out of them, coming from 3D space. I think this is a pretty cool exercise, and I've definitely done this process a lot myself to fabricate physical models out of cardboard, of glue or wood or that kind of stuff. It would be interesting to see the surface straight to a poly surface, like CLT panels join edge to edge and lay them flat. Each edge would have a unique angle. Yeah, but that is a bit more of a that's a bit more involved process, because now you have to curate the angles and the edges, and it involves a bit more of computation. But you're right, that would be really cool. Do we want to do tagging? Let's do some tagging actually. One last thing that I would like to do before we wrap up this exercise, is the fact that when we start working with this kind of definitions or this kind of modeling where each element is unique, it's individual, it's different from all of them, and we want to fabricate things, the problem of knowing which element is which and where it goes in 3D space becomes way more pronounced than if we're doing serialized or mass production. So tagging elements properly and giving them names or numbers or whatever becomes really important, because it's a way of keeping track of where each element has to go. So before we wrap it up, I would like to do a quick example of how to tag, how to give names to each one of these panels, and therefore be able to track them in the drafting, in fabrication, in whatever. We can, here in Grasshopper, we can go to the display category, and there are, in the dimensions category, there's a bunch of components that allow you to draw things like annotations, text, etc. in the view part. So one of the ones that I like the most is the text tag 3D, because it allows me to just create text in 3 dimensions that with a particular orientation. So what I'm going to do here is I'm going to say, I'm going to drop this component. I'm going to say, what is the location and the orientation of the text tag? And you can see how it's asking me for a plane. Oh my God, what a coincidence. I do have planes here for 3D panels and for the flattened panels on the top. So what a coincidence. I'm going to use these planes here to draw the text. And the text that I'm going to draw, for example, is going to be panel. So if I do that, you can see that I have some display text on the corner of each one of these planes saying panel. And I think there is a size component that I can also customize. So I can make the text smaller, bigger, and I can even change the color, etc., etc. But obviously, I don't want the word panel to be the same for all of them. I would like to have some kind of code that differentiates each one of the panels individually. So what I can do is that I can create a list of tags that is going to be unique for each panel. So for example, for the bottom ones, I could say, I'm going to create a code that is going to be B-0, B-1, B-2, B-3 to ID to tag each one of the panels individually. In order to do that, it's going to be as easy as creating a string. So where do I have string manipulation? Here, I have under sets, under categories, there is a category called text that I can use to generate, modify, manipulate, and do operations with text. So for example, I'm going to join here, I'm going to concatenate text. And the way I'm going to concatenate that is that the first fragment is going to be for example, B and a hyphen. Or I'm going to actually uppercase that. Oh, sorry. Uppercase B. So that's going to be 1. And the other one would need to be a list of numbers from 0 to however many panels I have. So that's going to be, I can create a series of numbers that are going to start at 0. The step size is going to be 1, so the default. And how many values I'm going to have in the series? The same amount of values as spans I have in my definition. So So that's going to be here. I'm going to have a list of numbers 0 to 10, for example. That's the number of spans. And then if I plug this in here, you can see that the result is a list of tags that go from 0 to 10. If I plug that into the text tag component, you can see that the tag is now B0, B1, B2, B3, blah, 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 all the way to B10 at the end. And then, so that can be one, and then I could use a very similar technique to tag the other ones, that are on the in-between, except that for those ones, I probably want to concatenate a different list, which is going to be, instead, it's going to be with a T. So it's going to be T hyphen, and then I'm going to use those as the text tags here. And maybe I move this here to make things a bit clearer, and maybe I move this here to make things clearer, and use the same slider for both. All right. And now you can see that I now have the tagged elements B0, T0, B1, T1, B2, T2, etc. And I could use these panels if I wanted those tags to also show up here in 3D space. I could also use them to make sure that I know where these panels are coming from. All right, and I think with this, I am kind of happy with this exercise. This was panelizing a facade in triangles in 3D space, and then taking those triangles and laying them flat on the XY plane for drafting or for fabrication or for whatever. All right. This involved a little bit of data manipulation and tricks. I hope this was useful, and this definition is definitely super useful for many things, such as for many things, for models, for drafting, and whatever. I hope this was useful. I hope we learned some data manipulation with this, and I will hopefully see you on the next video or the next exercise where I plan on doing this very similar technique, but instead of just on one surface with one strip of triangles, I would like to do it on a surface that has a two-dimensional strip of triangles. It's going to involve serious data manipulation, but it's also going to be super useful for all of us. Thank you very much, and if you like what you saw, maybe like this video, maybe subscribe to the channel, maybe turn on notifications, all those things. Thank you very much, and see you on the next video on this series. Yes, Michael, you can also just like leave a gap or do some offsets or whatever to account for the welding gap. That is absolutely true. And yes, Smith, if you make something cool, make sure to share it on our Discord channel or put a link on this video, etc. All those, make sure to share that work. I would love to see that. Now, I need to record the introduction to this video. And for that, I'm going to turn off these planes here. I'm going to turn off these nodes here. I'm going to turn off these two surfaces, and this here, and this here. I'm going to group this. I'm going to group this. I'm going to group this here. I'm going to group this here. And oops, I'm going to group all of this and then turn it off. There you go. And actually, I can now move this and I can, wow, how cool is that? Ah, I like that, actually. Okay, so let me record the introduction. Hi, this is Jose Luis, and welcome to another video in this series, Introduction to Parametric Modeling. In this hands-on exercise, what I would like to do is I would like to create a free-form facade starting from two random curves that I have modeled in Rhino, but I would like to create an algorithm that triangulates that facade into planar panels. And this is very important because very often creating nerves surfaces in the real world is very difficult and costly, but if we panelize them into flat planar panels, then making it out of glass, wood, metal, and any other material is a much easier thing. So in this exercise, I'm going to teach you how to create this triangulation, and of course it's going to be absolutely parametric, so we can control how many elements are in each direction. We can control the shape of the curves, so that we can adapt the geometry of the surface. And another trick that I would like to show you is now how to take all those panels that are somehow in three-dimensional space and reorient them to lay them flat on an XY plane, an XY plane, so that we make our life easier for drafting them, for putting them in drafting in plans, or for sending this to somebody who might fabricate them with a machine or like cut them in paper for making a model or anything. And because these techniques are the ones that we typically use when we do mass customization, being fabricating things where each element is different from the rest, tagging and giving these proper names so that we don't forget which element is which is actually very important. So I will also teach you like the small techniques about how to add labels to each one of the elements to make sure that we know which one is which and we don't lose track of them. So this exercise is going to be pretty cool. It's going to be very similar to the ones that we have done in the past, creating triangulations in three-dimensional trusses. It's just that instead of bars, we're going to be using panels. But it's also going to involve data manipulation and some other tricks that I'm going to show you through the exercise. So without further ado, let's get busy and let's do some triangulation. Have I mentioned triangulation is one of my favorite topics? Anyway, let's do it. Okie dokie. Oh, God. All right. So I think that's it. Oh. So it's been an hour and a half. How's everyone doing? How are we holding on? All right. So that was triangulated facade. Was this helpful? Did you like it? Now we're going to do morning of 27.5. That was triangulated facade. Now, the other exercise that I want to do is the same, but it's very similar. But it involves doing it in 3D, 4 panels. So, but I'm not sure. This might be a little advanced. This might be a little advanced. Is that true? All right, and perhaps for that, okay, I think we're just going to do it and see how it goes. And if it becomes too complicated, or if it takes too long, or if it just gets messy, then we will just not publish it. I think I'm leaning towards perhaps spending a little more time now in this live stream, taking it a little longer, and then finishing that up, and not live streaming this afternoon because I do have to sit down and plan what the rest of the live streams are going to look like. So I think we might do that. What is the time? Yes. Okay. So I think we're good time-wise. Let me take a quick break. I'm going to go get some water. I'll be right back. Mm, okay, so how are we going to do this? I think I'm going to record a small video in which I'm going to be talking about the Pathmapper, and then I will use that video. I will use that video to as material for the surface one, where we're going to need definitely the Pathmapper. We're going to need the Pathmapper. Okay. Okay, so let me save all these files. Start, and so this is going to be saved, and I'm just going to open from the stream files. I'm going to open the one that was data tree operations in Grasshopper. I'm going to open that, and I'm going to open that here, and I'm going to save that as advanced. Oh, you're not seeing me. Sorry, advanced data tree manipulation. Advanced data tree manipulation. And so that's going to be one, and then I'm going to save as here, advanced data tree manipulation. And here I'm going to still do some point lists. Okay, so that's going to be, it's going to be a lot. And then, so what do I want to do? I want to showcase the Pathmapper. The Pathmapper is literally my favorite component in Grasshopper, and it's the Swiss Army knife of manipulations at the level of the data tree. So examples that I would like to show. So for example, that's going to be 0, 0, A. And then that's going to be 0, 0, A plus 1. So that's going to be, that can be 1. And then we can see that if we do that, then the result is, let's compare the results. The result is that we have offset this branch 1 unit. So now, if I want to do, for example, if I want to do 2 times A, you can see 0, 2, 4. If I want to do, for example, just A, you know, just A. So we are simplifying the tree. Now, what if I want to flatten? This is like this. What if I want to graft? But if I want to graft, then I need to say 0, A, and I, and then this is going to be I. If I want to graft like that, and I want to flip the matrix. I want to flip the matrix, and that can be I and A, for example. That could be. Let me just copy. Let me just copy all of this on a separate file so that I can take a look. Thank you. Thank you, Michael. It is true. The Pathmapper is amazing. It's really, really cool. And what about an example where I use the constants? So item count, number of items in the current branch, path count, number of paths, branches in the tree, path index, number of index of the current path. How could I use this? Is there any way we can use the Pathmapper to drop branches? So Grasshopper remove branch Pathmapper. Oh, Alfonso Peluso has a video on.
Hello and welcome to my channel. If you've been here before, welcome back. My name is Alfonso.
Oh, I don't know Alfonso Peluso, but he looks like he has a lot of tutorials. Ah, that's nice. Okay, so we should check out Alfonso Peluso's channel. It looks pretty cool. Who is this gentleman? Ah, Illinois Institute of Technology. I see. Wonderful. That's great. So the Pathmapper and The cherry picker. I wonder.
All that path. Our best. Wrap. And then
He's doing the same thing. All right, he's doing the same examples.
we're almost done here.
The flat and simplify,
What they are
and the flip,
organized in columns.
and the flip
We're gonna go to
matrix.
another panel. So let's go ahead and plug that in.
Huh.
And
All right. So he's doing. All right. So I'm basically going to do the same video that he did. Okay. I think
before I show you guys that
minds are alike. Minds
what
are
if
alike.
I want to add branches. Copy.
Add or remove branch. Oh, I want to know how he does that. Add or remove branch.
Or lock those structures. And so now that branch structure is going to change. And if I need to add more, 0, me cherry picker, highlight.
Well, that's not exactly what I wanted.
By understanding this, you would have anyone. I learned from you guys. I learned from myself.
Okay. That's not what I was looking for. Alfonso Peluso, nice to meet you, sir. Greetings from Boston towards Chicago. All right, so yeah, so first about grasping organizers. Okay, creating data trees. All right, so this is not going to work the way I wanted. What if I only want to take A, and I just wanted to make this number so all of them would go into a branch number 2. Yeah, so I cannot really isolate this branch only. Lexer combo editor, is there? Grasshopper Lexer combo editor. Can you do logic here, like if else, if else? You can set multiple mappings in Pathmapper. What? Create null mapping. Create flatten trim. Oh no, create renumber. Oh, create reverse. Wait, look. Interesting. So it has like it has like different templates. Interesting. This is really interesting, actually. But I still cannot add multiple. How do I add multiple rules? I don't think I can add multiple rules, can I? No. Well, so we're not going to really remove data we're not really going to trim data out. Doesn't matter. Okay. So I'm going to is there anything I could learn? Obtaining path count, Pathmapper syntax. In case you want to do partition, Pathmapper. Wait, what is this? I divided by 5, I divided by 25. I see. Plus power. Here's all the operators. Exhausted. Okay. So it looks like the combo lexical editor uses the expression editor. So returns A if test is true, B if test is false. Okay, so we could do something like, for example, we could do an example where here we can actually, sorry, I'm doing a little bit of research here to make the video and to do interesting examples. So actually, and then here we could do, for example, we could do here power of a to the cube, for example. You can add various inputs. How can I add various? Baris, Benzel, welcome. How can I add various inputs to the Pathmapper? I don't know how to do that. How do I add multiple input paths in the editor? How can I do that? It doesn't enter? Oh, wait. Oh, as in, and then B. Ah, I see. Okay. Interesting. Wow, I had no idea how to do that. Thank you. Thanks a lot. I see. So that's power. Or, for example, I can do small conditions. So if A is equal to 0, then I think it's not going to work. That's going to be if A equals 0, then and then what? A, otherwise 4 times, well, that doesn't really make it, then minus 3, otherwise 3. This is a really stupid rule. What is the test? How do we do a test rule? How do we do? All right, just give me a second. I'm still doing a little bit of research, but and copy and paste below. All right, so all right. If x is equals 0, then -1, otherwise 1. Oh, wait, what? Ah, this is very strange. Ah. Huh. I see. So it uses the single equal signs. I had no idea about that. Operator equality. Yep, it's a single equal sign. Different, if this is different. Okay, I see. Yeah, no, doesn't work. We need numerical, we need numbers. I see. Okay, I think I'm just going to do a little bit of that. So we're going to do the Pathmapper, and I'm going to explain the Pathmapper, and after that, and then after that, so I'm going to make a video where I'm going to explain advanced data tree manipulation, and I'm going to be using the Pathmapper. I'm going to explain different ways we can use the Pathmapper to do things. So I'm going to be explain, and then I'm going to do several examples, and then I can, so for example, I can weave, I can do this, and I can weave them together. Because then I can just weave them here and weave them here. Huh. Interesting, yes. Okay. All right. So I'm going to keep this here as a cheat sheet, and then I'm going to remove all the stuff here. Okay. And then this, yep, okay, quiet. Okie dokie. So, all right, let's do this. Let's go for it. I'm ready for this. Oh, my battery. If I go mute, can you please let me know? Because I think I'm going to, my microphone battery is going to die. Hi, and welcome to this video. Hi, and welcome to this new video in the series Introduction to Parametric Modeling, where I would like to talk about advanced topics in data tree manipulation. Because I think we have seen like the two simpler ones, flattening and grafting before, but we haven't seen more advanced ways of changing the data, the structure of the data tree, etc., etc. Over and over again. Let's do it again. Hi, this is Jose Luis and welcome to another video in this series, Introduction to Parametric Modeling. In this video, I would like to discuss advanced topics on data tree manipulation, because in the previous videos we have seen how to manipulate lists, so how to work with lists at the tree level but not change the structure of the data tree. But at the same time, we have also seen the two most basic operations about how to change the tree structure, which were flattening and grafting. And you're going to be using them like 80% of the time. Those are the most popular by far. However, sometimes we will need to do way more fine-grained control manipulations at the level of the data tree. And therefore, we will need to have special tools in order to do that. If you go to the tree, if we go to the Sets tab, and we go to the tree category, we can see that there are a lot of components that do many things, such as like offsetting branches, retrieving branches, blah, 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 whatever. But in this tutorial, I would like to focus on one particular component, which is going to be the Pathmapper, which to me is like the Swiss Army knife of data tree manipulation within Grasshopper. So this is going to be specifically, a lot of what I'm going to be talking about today is going to be very specific about Grasshopper in particular and data tree structures. In other programming languages or in other environments, things work a little different, but it's going to be a super, super useful tool to discuss in this series. And especially, it's going to be useful because we're going to be using it in the next few examples that I'm going to be showing. Now, what is the Pathmapper? So if you remember, you have seen me rant long ago about how I like the expression component because it's very flexible and allows me to customize exactly all the operations in a very elegant kind of one-liner way. So to me, the Pathmapper is kind of the expression editor for data tree manipulation. It has a very, very similar spirit, and actually it shares like a little bit of the underlying code actually on the back end, as you will see very soon. The Pathmapper is if you will, is an editor that I can use to customize the operations that I do on a data tree. So what does that look like? Well, I can plug in here the Pathmapper, and then what I can do is I'm going to just plug in here a couple panels so that I can take a look at the structure of the data, and you can see that we're already familiar with this surface that has been subdivided in 3 collections of 4 points each in the UV directions, okay? And then what I'm going to do is I'm going to paste another component here, another panel, and I'm going to plug it in here. Because the Pathmapper right now is empty, you can see that there's no operation, have been no changes whatsoever to the data tree. But of course, we are going to change that a little bit right now as we double click on the Pathmapper. And as we do that, we get this pop-up called the Lexer combo editor, which again, if you will, this is kind of a text editor that it allows me to customize the combinations or the changes that I do to the data tree. How is this going to work? Well, on the left-hand side here, what you can do is you can type in a generic way what the structure of the data tree looks like right now. And then here on the right-hand side, also in a generic abstract way, and I will explain what that means very soon, I can write down an expression of that exemplifies how do I want to change that data structure. So what does that mean? If I look at what's coming in, you can see that what's coming in is basically a tree that has 3 levels, 1, 2, 3. The first 2 levels only have zeros, but the last level has a number that goes from 0 to 1. So representing this data tree in an abstract way is just as simple as opening and closing curly brackets, and then inside of it using variables to represent the level of each tree. So for example, if we have 3 levels, I can say whatever the number of the first level is, I'm just going to call it A. Then I'm going to write a semicolon because that's how they're separated. The second level, whatever that number is, I'm going to call it B. All right, and I'm going to add another semicolon. And whatever the number on the third level is going to be, I'm going to call it C. So I'm just giving it names. I could also name it first, second, third, for example. Actually, let me do that. First, second, and third. Actually, now I'm just going to go for A, B, and C because I find it a little bit more elegant. Whatever. So A, B, and C are going to be the names that are going to be given to the number of each one of the levels. And then what I would like to do here is I would like to write an expression that uses those variables to change the data tree. So for example, the first 2 levels are pretty boring because they're all zeros. But the last level is much more interesting because it has numbers that change from 0 to 2. So let's say that I wanted, for example, to offset all the branches by 1 unit. What I could do is I could say the target structure that I want has to be the same number for the first level, the second number for the second level, and whatever the third number for the third level is, just add 1 unit. And then let me close the curly brackets. If I press OK, you can see that the expression editor now shows here with the expression that I just typed. And also the tree, you can see that it changed from 0, 1, 2, it changed to 1, 2, or 3. So I can also do, maybe I can offset like 5 units, and now you can see how the branch is 5, 6, or 7. I can offset it negatively, for example, like this, right? And then it just goes back 1 unit, etc., etc. So with this expression, I have been able to take a canonical or an abstract definition of the tree with variables A, B, and C, and then represent the change that I want using those same variables and adding like a little bit of a mathematical expression to it, a simple algorithm. All right? What else can I do? Well, let me just copy paste all of this and I'm going to move it here. And for example, I can do things such as instead of adding 1 unit, I can double the number for the branch. So for example, I can say that is going to be 2 times the value of branch C. Okay? And if I actually, wait, let me show you something. If I do a similar operation, but instead of 2 times C, I do 1 plus 2 times C, you can see that the first was 0, 2, and 4, and now it's 1, 3, and 5. And take a look at this. If I were to now combine on an additional panel, for example, if I were to combine on a panel the first data structure here and the second one with the shift, you could see that because the numbers of the branches are now correlative, when they move into the branch here, you can see that they get ordered right away. And therefore, this data goes first, this data goes second, this list goes third, this list goes fourth. And therefore, implicitly, what I have done is that I have woven the branches of the tree one after the other on a one-to-one basis, like 1, 1, 1, 1, 1, something like this. Can you see my face or my? I don't think you need to see my face, but can you see my fingers? How this panel here, has woven with the other one. All these branches have woven like this, which it's a really neat thing to do. For example. So over there. So by doing a little bit of algebraic manipulation of the data tree, we can do operations such as, for example, weaving two data trees that have a similar structure. We can weave their branches. Another thing that I would like to, for example, highlight is that pretty much as the expression editor, the Lexer combo editor allows for advanced mathematical expressions. So if you remember from the expression editor, if we double clicked and we went to the expression functions, we did get this kind of pop-up that gave us a bunch of functions that we could use to calculate numerically, for example, advanced operations such as sines, cosines, square roots, absolute values, etc., etc. So these functions, these expressions, I can use them as they are in the Pathmapper. So they are compatible. They use the same lexicon. So for example, here I can say I want the third branch to be now the power of the base number to the power of 3. So the cube of that number. So 0 stays 0, 1 stays 1, and 2 goes up to the value of 8, right? Or, for example, I can say I can use conditional expressions. So for example, let me copy and paste all of this here. So if you look at here, you can see there's a small function called if, which says that the first part is going to be a test, and then if this is true, it returns the A, otherwise it returns B. So for example, here I could write I could write a condition if I open and I close parentheses, and then the first argument is the statement. So for example, if C is equal to 0, and remember that this expression editor uses single equal signs to compare things together, as opposed to, for example, many programming languages that use double equal signs. This one uses single equal signs. So you just need to remember that. And if C equals 0, then the branch name is going to be -1. I'm just going to hard code that. Otherwise, the branch is going to be, the level is going to be the value of 1. And if I do that, you can see that, what just happened? So here by doing that, because I hard coded the value, well, let me just do this first. So this is going to be C. So you can see that if the branch had the last level 0, then we turn it into -1. Otherwise, everything else stays with the same value. Okay, so I will explain what I just did in the next example. Now, what else can we do with Pathmapper? With the Pathmapper, we can do many other operations that are here common to the tree operations. So for example, let me show you one. I'm going to copy and paste this here. And very often, for example, we have the problem of branches having a lot of redundant information. So all these leading zeros, sometimes are just like, it just gets too big, it's kind of complicated. And actually, many components, what they do is that when you right click, they incorporate an option that is simplification, which if I do, you can see that the tree right away gets simplified into, and it removes all these leading zeros and everything that is kind of useless. So we can do we can do the exact same operation at the path level. So how would that look like? Can you think about this? I'm going to give you 1 second. You can pause the video if you want. So if what we want to do is remove useless levels that only have redundant information, like the first 2 levels only have zeros, then we have represented the first 2 levels with A and B. So the only thing that we need to do is, in the output, just don't use A and B, We only want branches that have the value of C in them. By doing that, we have effectively simplified the tree. Like that. All right? What about very common operations that we already know, such as, for example, flattening? Flattening, if you remember, meant taking the whole tree structure, removing all the branches and all the complexity information, and ended up with one single branch that had a 0 and with all the elements in the same list. What does that look like here? Well, turns out that we have used variables to represent the numbers that are coming in at the levels of the paths. But it turns out that there's actually no real need to use that on the target. What we can say is like, whatever you're giving me, whatever the data structure here is, I don't care. What I care is that the structure of the output has to be one single branch. Everything has to go. Everything has to be mapped from whatever you were here into this one new branch that is going to have the value of 0. And if I do that, the Pathmapper automatically takes every single of the items and just in order feeds it to this new branch called 0 that is not respecting or incorporating at all any of the logic of the incoming data tree. Therefore, this is a manual way of doing flattening with the Pathmapper. What about, well, you probably know where I'm going with this right now, right? So what if I want to do grafting on the other end? Well, grafting is a little bit more complicated, but it's not really that big of a deal. How could we do grafting? If you remember, grafting was an operation where we took the data tree and then we added a new level. And for each level, we created a new level for each one of the items that we had on the list. And if I do that here, so let me graph that tree. If I graph the tree and I compare the grafted tree with the original one, what we can see is that now each element has its own branch. And we can also see is that the branch has maintained the first 3 levels. So for each item is contained in a branch that has the first 3 numbers being the same one as they were before. But the only thing that we have added is added a 4th level that has numbers going from 0 to 3, 0 to 3, 0 to 3, which also, if you look closely, happen to be the numbers that are the index numbers for the original items. So if we want to do a manual graft, then basically what it means, grafting is maintaining the data structure of the levels and adding a 4th level where each element is now on a 4th level which has the value of its index number. That is roughly the high-level idea. How can we do that with the Pathmapper? Well, I have said before that when we're using the Pathmapper, we can here, conceptually, we can describe the structure of the data that is coming in. But we can do that not only with the curly brackets representing the data tree, but additionally, we can capture the value of the index number of every item by using the parentheses and then using another variable to capture that number. I'm going to use I because I is a very typical name for referring to indices. And then what am I going to write here? I'm going to give you 2 seconds to think about it. Pause the video. And then, yes, you probably guessed it already. I would like to maintain the structure of what's coming in. So A, comma, B, semicolon, C, semicolon. And then now the 4th level is going to be whatever the number, whatever the index number of what's coming in, it's going to be. And as I do that, then I'm going to hit OK. And then you can see now how each one of the elements has landed in a new branch that maintains the first 3 levels And the fourth level is now the index number. Right? So this is grafting manually using the Pathmapper. The battery on my lights is gone, so let me please plug here. Oh my god, I'm tired. Oof. There's a lot of streaming today, huh? And what else do we have? So we have grafting. And we have flipping. And the last operation that I would like to teach you how to do with the Pathmapper is going to be called flipping the tree. Ooh, what does that mean? So let me show you. So if we go back to the where we were coming from originally, which is this surface that we subdivided into 3 families of 4 points, remember how when we talked about, I'm going to hide the surface. Remember how when we talked about data matching and blah, 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 I discussed how the operation of components work mostly at the level of lists. So if I now try to create, for example, interpolated curves with the data that is coming from this component, which remember is 3 branches of 4 points each, because components work at the list level, what's going to happen is that this component is going to create 3 curves, each one of them going through the 4 points of this data tree. Correct? Now, you may find yourself in a situation where this is cool, it's good for you, yet for some reason, instead of creating the curves in this direction, in the direction that we have naturally subdivided the surface, we actually wanted to create the curves in this perpendicular direction, or we wanted to have both. We wanted to have a grid of curves in 2D, which is a very common thing to need to do. So how could we do that? So maybe changing this? No, it's only changing the subdivisions. Maybe taking this surface and flipping it and then subdividing it again in the other. It gets a little complicated. So actually, the easiest way to do it is by taking this data tree, and instead of arranging the 4 points in this branch, 4 points in this branch, and 4 points in this branch, we may want to restructure the data tree and have a list that is these 3 points, another list that is these 3 points, excuse me, another list that is these 3 points, another one that is these 3 points. Let me go get some water, please. I'll be right back. Okay, thank you. That operation can be done out of the box with a component that is called flip matrix that is coming from the tree category. So what I can do is I can take this, whatever the data is coming like this, I can take that data tree and then I can flip it so that the structure now looks a little different. So now instead of having 3 branches with 4 elements, I have 4 branches with each element. And if you see the first element here, the first element is the second, the first element is the third, and then the second element is the first one here, the second element is the second one here, the second element is the third one here, etc. And if I do that, you can see that now the curves are going in the other direction. And if I plug this in here, you can see that the indices have also changed. This is the first one, second one, third one, first one, second one, third one. So this is the normal, the regular points, and these are the flip points. So, but if we look closely, what has happened here is that basically every element that had an index of number 0 has now landed in a branch that has the last level being the number 0. Every element that had index number 1 has landed in a branch whose last level is that number 1. Every element that has number 2 landed in 2, and every last element landed in a branch whose last value is the value of 3. So in a way, what has happened here is that we have taken values, we have replaced the last level of the tree with the index value of these elements. So if we want to do that operation manually, it's going to be as simple as doing that. So it's going to be as simple as taking, where am I? Taking this input, the input that we have used, so the 3 levels A, B, C, and the index in parentheses, and then probably just removing the third level and using as the third level the value of the index number. So if I do that and I press OK, you can see that now I have the exact same effect. And if I interpolate with a curve with these elements, you can see that all these elements are now going in this direction. And if I use the point visualization, you can see that the distribution of the indices is also the same one: 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, etc., etc. So, that was a lot. So I hope this was not very overwhelming, but this is just to say that the Pathmapper is basically one of the most versatile ways that we have of working with data trees in Grasshopper and making operations that affect the level of the tree of data in a more customized, in a more fine-grained way. There are some operations that we still cannot do with a Pathmapper, or maybe I don't know how to do them. I'm not entirely sure about that. Like, for example, completely removing a branch or removing elements from a particular branch. I'm not sure that can be done with a Pathmapper, but we already know other techniques to remove elements from a list, etc., etc. So we can rely on those, or we can rely on some other specific components here under the data tree category. So it's always my recommendation that you have no fear to just drop in components, checking them out, see what they do, and it's actually a really, really good way of learning more of how to use Grasshopper. So I think with that, I'm going to leave it here. This was advanced data tree manipulation in Grasshopper using the Pathmapper, the Swiss Army knife of data tree manipulation. And I hope this was useful, and it is definitely for us going to be useful down the road in this series for some of the exercises that we will be doing in this series. So if you liked what you saw, maybe like this video, maybe subscribe to the channel, or just say like a couple of words of gratitude in the comments. We're always happy to hear your voice and to get to know each other. Thank you very much, and I will see you on the next video. Bye-bye. All right. Okay, that was a lot. I don't think I can do the exercise that I promised I was going to do. Boo, Jose. Boo, Jose. You're welcome to give me a thumbs down if you will. Okay, I'm going to have to go because I have meeting this afternoon. I have to prepare content for the next stream. So because like I know that the next exercise I want to do is going to be the triangulation of a roof surface of sorts, but I don't know what I want to do after that, and I don't know how I want to wrap up the series. So I think instead of live streaming this afternoon, I think I'm just going to spend time on my own thinking about that, because I think maybe we could do that on the live stream, but maybe it's going to be boring for people. Folks, would you like to just sit down through a stream and like see me planning the next streams? Is that useful? Is that nice? Do you want to hear that? Do you not want to hear that? I also kind of feel doing that. I kind of feel like conscious. Poof. Let me save this stuff here. I'm going to save this file for the record. I'm going to group this stuff. I'm going to group this stuff. Oh, I forgot to do the enter and the more rules. Yeah, that sucks. Expression editor, advanced tree manipulation. That's going to be here. Going to be here. And I think that's fine. And I want to save this. I already saved it. So boom, out. And then, okay, so as I said, I think I'm going to take the afternoon free and sit down and plan the rest of the series, what exercises we're going to do and what are we going to be talking about. Is mostly probably going to be just a few notes on intersections. What else? Intersections. We're going to do intersections. We're going to do randomness. I want to do a few exercises on randomness. And what else are we going to do? Yeah, I don't know. What topics do you want to see? What topics do you want to see? So in Rhino, what topics should be left here? Oh, meshes. We have to do a little bit of meshes. You're right. Meshes. So let me write that down actually. Randomness, intersections, meshes. We need to do a little bit of meshes. Planes, grid. We're not going to do fields. Not interesting. Primitives. We've seen a bunch of these. Surfaces. We've also seen a bunch of these. Meshes, physical region, shapes, intersections, transformations. We've seen them. Visual, and then everything else is just plugins. Oh, maybe we could talk about Machina, huh? How cool would that be? Okay. What is sub D? Andres? What is sub D? Oh. Hmm. Subdivision surfaces. I'm not sure what you mean by that. Is that a technique? Is that a component? Or is that a new thing that they published with Rhino 7 or something? I don't know, but I'm not sure that it's a topic that it's general enough to make a section out of it in an introductory course. Yeah, guess what? I'm not sure what this yes is about. Okay. It's subdivision modeling. It's new with Rhino 7. Yeah, I don't think it's maybe we can do like a geometry jam or like an algorithmic modeling challenge or something with subdivision, but not really. Not really. But not really a full section in the list. So we're going to put a pin on that one. So I think it's going to be randomness, it's going to be intersections, and it's going to be meshes. And with that, I mean, it's already going to be like a super comprehensive introduction. So I think I'm happy with that. Well, we're going to leave it here. Thank you very much, everyone. I'm going to go. Remember that I think there's a live stream scheduled for this afternoon, but it's not going to happen. So I'm going to cancel that. And we will be back here tomorrow. What, 10 a.m.? We'll be here tomorrow 10 a.m. and doing more 10 a.m. my time, Boston time, Eastern, American Eastern time. And we will do more of this. Thank you very much. Thanks to everyone who's on the chat. I appreciate doing this in the company of human beings. And I will see you on the next stream. Bye-bye.